Okay, let's begin. So I'll fire up a slide pack. I hope you can see the slides and hear me clearly. Can someone just confirm? Can someone confirm if you can see the slides and hear me clearly? Okay, excellent. Let's begin. So, earthquake is not today's phenomena, right? It has been there since human civilization. Since the time actually Earth formed, but then since the human civilization, people started feeling it, and there were lots of myths and legends around why earthquakes occurred. So I'll read some of them. Say, for example, in Hindu mythology, people used to think then when one of the eight elephants that carry the earth gets tired, and nods his head, that is the time when earthquake happened. Uh, as per Mongolian mythology, when a frog carries the world moves. As per African mythology, when a giant on whose head we all live sneezes and or scratches, that is the time we do see earthquakes. Yeah. As per Japanese mythology, when the attention of god Kashima, who looks after the giant catfish Namazu that supports the earth and prevents it to sink into the ocean, weakens, and Namazu moves, that is the time you get earthquakes. Uh, and when a good Maimas decide to count the population in Peru, his footsteps shake the earth. Then natives run out of their hearts and yell, I am here, I am here. That is also causing earthquakes. So these are some of the myths and legends that people used to think before the modern science developed, uh, that something was shaking, yeah, and that was manifested in terms of earthquakes. But that had been a cause of worry or cause of concern, and people were threatened by earthquakes since prehistoric times. Okay, but we know now that earthquakes do not happen for such causes. Earthquakes happen by faulting. And what is a fault? Fault is nothing but the creation of a discontinuity or the creation of a fracture system inside the earth. And fault is a weak zone separating two geological blocks. The tectonic forces cause the blocks to move relative to one another. Okay. And based on their relative movement, sense of relative movement, we can divide faults into three categories. I think you know about them: normal fault, reverse fault, or thrust and strike slip fault. Of course, we talked about three stress regimes: normal stress regime, reverse stress regime, and strike slip stress regime. They are associated with such faulting. So normal stress regime is generally associated with normal faulting, where SV is maximum or vertical stress is maximum. Then the reverse stress regime is associated with reverse faulting, where S capital H is maximum and SV is minimum. And then strike slip faults are related to strike slip stress regime, where S capital H is maximum, SV is intermediate, and S small h is minimum. We talked about these three stress regimes, and now we are associating them with these faults. Why they are associated with this particular type of faults, we will learn later on during our structural geology classes. But for the time being, it's enough to know that these three stress regimes are associated with these three kind of faultings. Okay, so how faulting is related to earthquakes, and that is explained by a famous theory which we call the elastic rebound theory. So before we get into an elastic rebound theory, the explanation of the elastic rebound theory, you can see here an earthquake that happened due to the movement of the San Andreas fault, the picture to your right. Uh, the earthquake that happened in San Andreas fault, and you can see that the fence has actually moved. It's like a strike slip movement. So the fence used to be together, these two fences used to be together, and the earthquake along the San Andreas fault essentially moved this particular fence. It's a pretty pictorial representation of the surface expression of strike slip faulting. So what is elastic rebound theory is all about? Say, for example, you can observe here, prior to faulting, the road is straight. So this gray strip within the ground, suppose is the road, or in this particular case, we can also call it a geological marker. So we are trying to look at the displacement of this geological marker before and after earthquake. Okay. Now, due to the buildup of stress and why stress would build up, we explained that before, that there are three causes, of course. Uh, one is essentially your tectonism, the other one is the weight of the rock, and the third one is, of course, the fluid pressure. There are areas where stress can eventually build up slowly but steadily, and that buildup of stress essentially results the accumulation of strain energy along this weak zone, accumulation of the strain energy along this weak zone, deforming the crust. And then once, that strain energy, the strain essentially crosses the yield limit or the elastic limit that we had talked about, uh, the material ruptures, the material fails, or the material essentially breaks. In a normal language, in a layman's language, the Earth's crust essentially breaks into fractures or into two blocks. And while that break takes place, the strain energy, what was accumulated within the crust, gets released, gets released. And the manifestation of such energy release is actually earthquake. Okay. So it's the manifestation of the strain energy release is earthquake. And after earthquake, of course, the elastic rebound results in offset of along the fault, and then the stresses are relaxed. Okay, so it's like this: there is a stress build up, the strain energy accumulates, and once it actually touches the yield strength of that material, and then that particular material actually ruptures, and then again the stress clock is again reset. But the strain energy which is actually released is manifested in by earthquakes. Okay, so this is exactly what we have been just talking about. This is I don't need to speak about it once more. Uh, this is how faulting takes place, and then as a result, earthquake takes place. Now, earthquakes can happen pretty much it can happen at any depth. Okay? Can happen at any depth. For example, here you can see that the earthquake in the picture to your right, the earthquake's focus is at some particular depth, and this particular focus we call it as hypocenter. Okay, that is the center of the earthquake. That is the place where this elastic energy is being released, or the first, that is the source of the earthquake, and this is what we call as earthquake's focus, or also the hypocenter. Now, if we immediately project that particular uh, hypocenter onto the ground, that is what we call as epicenter. So remember these two definitions: what is an hypocenter, what is an epicenter. If an earthquake that happens at the surface itself, then the hypocenter and the epicenter are the same. But if the earthquake happens at a depth, then uh, the horizontal projection onto the ground surface of the hypocenter is my epicenter, right? Now we talked about two body waves, P waves and S waves. Now we are going to introduce you to two types of surface wave. One we call as the Rayleigh wave, and the other one is called the love wave. Okay, and we said that the depth of penetration for such waves is only limited to maybe 1 or 2 meters from the surface. Okay, so it doesn't penetrate deep. That's why they are called surface waves. Okay, so the Rayleigh wave, you can think of the motion of the particle is simply like, I'll give you an analogy. So you have a bed sheet, and we below that bed sheet, suppose you have a ball which is rolling. Okay, so there is a ball which is rolling from one end to the other end of the bed sheet, and the wrinkles that you will observe on your bed sheet is exactly like how the Rayleigh wave works. Okay, so it's simply like there is a motion of the ground, as if there is a ball rolling beneath the surface, immediately beneath the surface. Okay, and then love wave is slightly different. Love wave is, you can imagine this picture. You can think that the top surface of the earth is like some of these elongated blocks, and these elongated blocks moves perpendicularly to the direction of the lava wave propagation. But of course, the movement of these blocks is not essentially on the vertical plane, but they are on the horizontal plane. Okay, so this picture is a nice representation of how lava wave works. Okay, so I hope you could understand physically how Rayleigh wave and how love wave, essentially how the ground motion would look like for uh, such waves. Now, of course, their amplitude would diminish with depth. Okay? They have large amplitudes, and they are slower than body waves. Okay, that means um, the velocity is low, but their amplitudes are fairly high, and they are dispersive wave. So large periods are faster. Okay, so if you have a higher time period for each of these waves, they move faster. That's why they are called dispersive wave. But I hope you could understand the physical movement process of the Rayleigh wave and the love wave from these two beautiful cartoons which are drawn in the slide. Now, how do you record an earthquake? And that is what we call as observational seismology. Okay, so we are now equipped with to start recording and locating earthquakes. For that, we need seismic networks as of seismic network of as many stations as possible. So you can see here, you know, in this particular area, and you can see. Don't worry about the yellow color and red color. That's not. We don't really want to get into such details. These are planned. Some are planned. Some are operating, And these are the network of seismic stations or seismometers that can record earthquakes, okay? That can record ground motions due to the earthquake. In India also, there are plenty of such seismic stations which are installed. I think recently there was another seismic station that was installed by Ministry of Earth Sciences near Bhopal, or they're planning to actually. I don't know, that got actually delayed for COVID-19, but there are plenty of seismic stations or seismometers installed around India as well, okay, which can record earthquakes. So minimum number of seismic stations that are needed to locate the position of an earthquake epicenter is 3, and we will explain why is that. Okay. Now, before doing that, we need to understand a little bit about the velocity of P wave, S wave, and uh, surface waves. Okay. So now, what essentially happens that we just draw something for you. Come back to the slides. So I'll briefly explain how a seismometer works, okay? Give me a moment since till this whiteboard starts. Oh my God, bad news. See if I have a PowerPoint presentation. I hope this will stay just for a while. Let me see. Let's hope that it will stay like this. Okay. So how does a seismometer work? So what seismometer measures the amplitude of ground motion. Amplitude of ground motion. Okay. And I'm not getting into the details. You can read it from Lowry's book. But what actually happens that in earlier days, there was like a paper roll which was constantly rolling, okay? Which is constantly rolling. So there is a movement on a paper roll. Okay? And then there is like a needle which is fixed, and that needle is keep on, drawing lines. Okay, because the needle is fixed and the roll moves actually. Okay, keeps on drawing lines. Okay, and the needle is extremely sensitive. So as soon as there is an earthquake, okay, that needle actually starts to give a jerk. Okay, and then that jerk is kind of recorded. Okay, and then of course it again starts to run smoothly. Maybe another jerk. So nowadays, of course, this has become digital. No one uses a paper roll seismometer, But then this is the basic philosophy. There is a needle which is extremely sensitive to ground motion, okay, and then that is kind of so I mean attached to a rolling paper, and that as as soon as there is some sort of ground motion, that needle starts to jump up and down, and that you know is reflected by the uh, by the uh, by the uh, wiggles that you observe in your on the graph. Okay. Now, of course, if the ground motion is higher, okay, then I will see the amplitude is also higher. Okay. If the ground motion is small, I'll see smaller amplitudes. Okay. This is the basic philosophy by which a seismometer works. Now you can see the picture here. You can see the picture here, that this is the flat line of the seismometer. And then what is the fastest moving wave? The fastest moving wave is the P wave. So as soon as the P wave comes, I see a jitter. And then it becomes, like not as flat as it used to be, but then more or less flat. And then as soon as this S wave appears from the same earthquake, I see another jitter. Okay? And then, of course, the surface waves arrives, and I see the third jitter. Now you can see, of course, that so what it means that the P wave runs fastest, then the S wave arrives, then the surface wave arrives. But of course, the amplitude of the surface wave is way larger than if you compare it with P wave and S wave. Okay, so accurate absolute timing with a precision of 0.01 second is essential for seismology. So it's absolutely important that the actual time at which this particular it receives the signals are very very precise. Okay, and another thing that I want to take I want you to take in account is the difference between the arrival time of the P wave and S wave. Okay, so when does the P wave hits my station and when does the S wave hits my station, and the difference between these two, the time difference between these two is absolutely important in earthquake seismology. Okay, so the time interval difference between P wave arrival and the S wave arrival, remember, that is what we are after. Okay. Now, let us think of a situation. Just escape and understand this in a bit better way. Suppose this is my epicenter. Okay. Epicenter of an earthquake. Okay? So you can think that the epicenter is like the surface source of the earthquake, which is happening at the bottom. Okay. Now, for example, I have my seismometer 1 here, seismometer 2 here, seismometer 3 here. So this is placed at a distance of, so disturbing, D1, placed at a distance of D2, and this is placed at a distance of D3. Okay. And maybe I have kept another seismometer, which is S0, yeah, which is just immediately above the epicenter. Okay. By chance, I have kept it. That doesn't generally happen, but I'm just for the sake of understanding, I'm doing it. Okay. Now, so as soon as there is this elastic collision happening, what is happening? My P wave and this wave is starting to transmit. Okay, and P wave is moving faster. P wave is moving faster. and S wave is moving comparatively slower. So at S0, I mean the distance d is 0, right? So P wave and S wave will kind of, the P wave and S wave will kind of, uh, let's demarcate P wave with a different color and S wave with different color. So let's say P wave is red and S wave is black. Okay. So at S0, what would happen? P wave and S wave will be, coincident with each other, right? Now, at S1, of course, it has to travel a distance d1. So that means the P wave will appear fast, and then S wave will appear after a while. Here they will be coincident, okay, after a while. Now, larger the distance, the difference in time of their arrival would be keep on increasing, right? No, maybe I have to go beyond the board, okay? So larger the distance, so I can essentially say that D, yeah, is directly proportional to delta T P minus S, right? So the arrival time of the P wave and the arrival time of the S wave, the difference between them is directly proportional to its distance. Okay. So with that philosophy, let us look at this graph. So at 0, of course, is my epicenter. Okay. And then, say for example, this is this is seismometer A at seismogram at station A, seismogram at station B, at seismogram at station C. Now, just by looking at the nature of the P wave and S wave arrival, I immediately know that A is closest to the epicenter, B is little further than A, and C is farthest from the epicenter. Okay? Now, of course, if I join these lines, there will be a point where they will meet. Okay, there will be a point where they will meet, and that would be the point of the epicenter, right? Where there will be no separation between the P wave arrival and the S wave arrival. Now, of course, if I you know uh, take a do a delta x by delta t like is done in this particular, delta x by delta t like done in this particular graph, you should be able to calculate the velocity of the P wave. Okay, you should be able to calculate the velocity of the P wave, and similarly, you should be able to calculate the velocity of the S wave as well by taking in account the time interval after which it arrives. Right? Is this point clear to you all? How to calculate the P wave and S wave velocity from
Sir, in the plot, what is the x and y axis?
hang in for a moment. I am in a class. I'll talk to you later. So x-axis is the distance, na? Distance from the epicenter. And y-axis is the time difference between P wave and S wave arrival at each of these stations.
Okay, sir.
Yeah. That's the fundamental. I mean, that's where we started, right? Any other question? Was it clear for you? The philosophy is clear for all of you? How the velocity of P wave and S wave is calculated? What is the importance between the time of arrival of P wave and S wave. Was it clear? Ashwin, was it clear for you? Excellent. Because you can expect questions from this particular topic, even in your net exam. In your net exam, GSI, GATE, whatever you are sitting for, you can expect questions from this particular topic. They will give you some velocities and stuff, okay, or the time of arrival and everything, and then you have to calculate your velocity or the epicentral distance or things like that, okay. So, but this is very simple unitary method that you have to apply, but it's important to understand the philosophy, okay. I hope it was clear for you. Okay. Now you are looking at a real example, okay, and you can see, of course, there are plenty of seismic arrays, I mean seismometer arrays, and you can see the arrival time between P wave and S wave is keep on increasing if we are moving from 1 to 8, okay. Yeah, and these are actual real data. And so by looking at this, I can simply say I know that. So if I look at this one, uh, which one is closest to my epicenter, 1 or 8? Answer me, guys. Which one is closest to my epicenter, 1 or 8?
So one.
One, absolutely right, because the arrival time of the P wave and S wave is the difference between the arrival time and P wave and S wave is smallest in one. Okay. Now, if I want to do the epicentral distance stuff, what can I do here? Let me just take a snip, and because this is a PDF, and then I can draw it for you here. It's very simple. Okay. Now, if someone asks me, tell me where my epicenter is, okay? So, what I can do, I can just simply, join these P waves, arrivals, join these S wave arrivals, and see where they kind of meet. Okay. This is a rough job, but you can do a better job, of course, if you have computer properly. And then, this is perhaps your epicenter. Yeah. This is where perhaps your epicenter is, because this is the axis where my distance is, and this is where my arrival time is plotted. Okay, I hope this is clear for you. So, if I want to exactly pinpoint the location of a particular earthquake's epicenter, okay, I will need to have three, uh, at least three uh, seismometers. Okay, so after we know the distance of the epicenter from at least three stations, we may find the epicenter like this. Okay, so you can say, with P wave velocity, that the arrival time of P wave velocity, um, using the standard velocity of the P wave, you know that it has traveled. The distance of the epicenter might be from this seismometer at a radius of 2,800 kilometers. So I draw a circle. Maybe from this particular seismometer, it is at a radius of 4,800 kilometers. And so there is one seismometer which is situated in in North America, another in South America, and another in the coastal Europe. And then you can see 4,800 meters from the coastal Europe, 3,400 kilometers from South America, and from North America, it is around 2,800 kilometers. And then I draw three circles. Where these three circles meet, that is exactly my point where earthquake perhaps has happened. Okay, that is my uh, earthquake epicenter. Okay, I hope you understood. So what I mean, let me just, if not, let me just try to explain once more this point. Yes, so I have three seismometers. Okay, so I see my, say for example, my P wave after the earthquake has happened, the P wave has appeared maybe after a few seconds, T1 seconds. And then by calculating the standard velocity, I know that the epicenter would be at a distance of, say, x1 kilometers. Okay. Okay. So I draw a radius with x1 kilometers. Maybe from doing the same with the same philosophy, I know it will be at a distance of x2 kilometers. So it will be on this circle on x2 kilometers. And then this is x2. Okay. And from seismometer 3, I know it has happened maybe at a distance of x3 kilometers. X3. So then I know where these three circles meet. That is where my earthquake must have happened. That is my epicenter. All right. Now, there is something called how to determine the magnitude of the earthquake. And you are very much familiar with the term that, you know, earthquake's magnitude, you always hear it in the newspaper. 3 magnitude earthquake, 4 magnitude earthquake, 5 magnitude earthquake. And that magnitude earthquake is essentially expressed in Richter scale. And the Richter scale was first defined by Charles Richter. Okay. And we were going to show you how this particular magnitude is actually calculated. Okay. So pay very good attention to it. Okay. So besides the position of the epicenter and the depth of focus, the earthquake magnitude is another defining element for each earthquake. Okay. So depth of focus is is the difference between the epicenter and the hypocenter, right? It's at how much depth your earthquake has happened, right? That is the depth of focus. And the other one is the distance of epicenter. That is what we just discussed. So how to calculate the magnitude? So magnitude defined by Charles Richter is proportional to the amount of energy released from the focus. So it's a very important parameter that is a direct manifestation or indication of how much uh, seismic energy that was, or strain energy which was accumulating before the earthquake has been released. Okay? So magnitude is calculated from the amplitude of the ground motion as measured from the seismograms. Okay? You also need to know the epicentral distance to take into account. Okay? So what I'm doing here, I can take any magnitude, but for this particular example, I'm taking the S wave magnitude. Okay, because it has a higher magnitude, So what happens that it has a higher resolution as well. Okay, so I'm taking the S wave magnitude, and you can see here in this example, it is around 23 millimeter. Okay. Then I put it in this particular plot, which was actually proposed by Charles Richter. Okay. and it has three scales. One you can see here is the difference between the arrival of S and P, uh, S and P wave. Sorry, yeah. So the arrival time difference between the S and P wave, and then this is the amplitude. Okay. So what I'm seeing here, say for example, the amplitude is 23 millimeter. Okay. So amplitude is 23 millimeter. That means I am here. Okay. And then I am looking at the what is the time difference between S and P? The time difference between S and P is, say, for example, in this particular is 24 seconds. Okay. So I go 24 seconds. Okay. I go 24 seconds. So then I join 24 second with the amplitude 23 millimeter, and then it actually essentially intersects at 5, okay, in the magnitude scale. So I say that the magnitude of the earthquake is 5. Okay, so this is a very simple calculation by which you can calculate the magnitude of the earthquake by using the amplitude of the ground motion and the difference between the arrival time of the S and P wave. Okay, as simple as that. Okay. Now, of course, if the amplitude would have been lower with the same S and S minus P uh, interval, S minus P time difference. Okay, I can see the magnitude, the magnitude would be lower as well. If the amplitude is lower, the magnitude will be lower. Now, what are these? AF stand 0, 5, 40, 60 kilometers, 100 kilometers, 200, 300, 500 kilometers. This is essentially this is the epicenter, and these are the distance from the seismometers which are there, which have been recording. So why there are 240? 240 is because, from the same epicenter, you can have, 140 in maybe northeast 30 degree, in another in northeast 60 degree. Okay, so in two different directions. So that's how, and we have got this particular record in perhaps in the so that is what is shown in this particular epicentral distance, but which is not particularly important in this calculation. But you can you can imagine what I need essentially is the difference between S and P second, which I'll plot here, and then I will plot my amplitude here, and then I join them with a straight line wherever it actually intersects my magnitude scale. That is the magnitude that I will use. Now, how this plot was made? This is purely empirical. Okay, this is purely empirical. So there is no rocket science behind it. This is how conventionally Mr. Charles Richter has actually proposed to define the magnitude of the earthquake. Okay, which takes in account both the difference between the S and P arrival as well as the ground motion amplitude. Okay. So you can also use this formula, of course, where m is equals to log a plus c1 log d plus c2, where a is the amplitude of the ground motion, d is the epicentral distance, and c1, c2 are constant. This is how you can also calculate it. But the more graphical representation is the one that I have just expressed. So there are many types of magnitudes in seismological practice depending on which waves to measure the amplitude. ML, MB, MC, MS, MW. Let's not be bothered about them because they are fairly complicated at this moment. We might discuss them later on, but for the time being, don't be too bothered about them. Right now, just be just MW. That is the one which keep in your mind. That is the most referred magnitude, which we have just explained. Okay. Increase in one order of magnitude, okay, that means 32 times more release of seismic energy. This is a very important statement to remember. Okay, so what it means, say for example, if I have 5 magnitude earthquake happening tomorrow at Bhopal, and if we have a 6 magnitude earthquake happening tomorrow at Bhopal, okay, the magnitude of this energy that will be released, seismic energy that will be released, or acoustic energy that will be released, is 32 times. Okay, so 5 magnitude earthquakes happen. You know 4 5 magnitude earthquakes happen everywhere. We even we feel a little bit of shake. We are happy, no problem. But as soon as it starts reaching 6 7 7 is completely devastating. I mean it completely destroys the city. Okay, six is also not good at all. Okay, so why does that happen? Although the magnitude difference is only one, but the energy that will be released, the difference in energy release is almost 32 times if we have one magnitude of earthquake increase. Okay, so this is the last slide for today, and we will stop the discussion, and then we will continue in the pre-recorded lecture, of course. Okay, so if the magnitude is less than 2, it's not felt by humans, recorded by instruments only. If the magnitude is 2, felt by the most sensitive suspended objects that swing. Now, there is something which you need to see here, which is fairly important to understand, and we'll explain why later on. That if I have a larger magnitude earthquake, if I have larger magnitude earthquake, their frequencies are actually decreasing. Okay, so smaller earthquakes happen every day in numbers, in numbers. We don't even feel them. But then the higher magnitude earthquakes is the one that matters, but they happen rarely. Okay, that is a good that is something that follows a very beautiful law of nature, which we will see, which we call fractals. Okay, and because the earthquake magnitude and its frequency are fractals, that is a what is that called? It's a bless to the living creatures of the world. So the mother nature has been blessed to make the earthquakes to being fractal, so that the higher magnitudes are rare and smaller magnitudes are numerous, simply because one magnitude of earthquake increase means 32 times of seismic energy increase. Okay, so 3 magnitude. So 2 magnitude happens almost like numbers per year. You can see 1 into 10 to the power 6. Okay? And magnitude 3 felt by some people, vibration like a passing vehicle, happens around 100,000 per year. Magnitude 4 felt by most people, hanging objects swing, dishes and windows rattle and may break, around 12,000 per year. 5 magnitude earthquake felt by all. People are frightened. Chimneys topple. Furniture moves. Around 1,400 per year. 6 panic. Building may suffer substantial damage. Around 160 per year. 7 to 8 widespread panic. Few buildings remain standing. Large landslide. Fissures in ground. I mean fractures. The ground actually breaks apart. Around 20 per year. 8 to 9, complete devastation, ground waves. You can see the ground actually, the pictures that we saw for Rayleigh wave and love wave, you can see them with your naked eyes. So number, rarely, maybe one, some years there are none. This is an average around two. Okay, but there are years where there are no such earthquakes. Okay, so the important thing to remember that larger the magnitude, that means the energy increases exponentially, 32 times per increase of one scale of magnitude. Okay. And so, proportionately, I have more devastating effect on human civilization. But the bliss is essentially that their numbers also decrease. Their frequency is not as high as they are for smaller magnitude earthquakes. Okay, so this is where I will stop today, and I will take any questions that you might have.
So, sir, two questions. One was regarding the amplitude, and so do we take the ratio of that and we compare it, the height versus the distance between the P and S?
Which ratio I did not understand
In
properly.
the plot, the Richter scale, that.
This one, okay. Uh-huh.
So in this, is there any significance of taking a ratio of the amplitude and the
Which a ratio between which two?
the amplitude, that is the height of that peak S wave, and the distance between the uh, P and S?
No, you just take the amplitude of the S wave.
Okay.
You just take the amplitude of the S wave and you take the interval between P wave and S wave. Okay, the time difference between P wave and S wave, and you plot them in this graph. Wherever that intersects is your magnitude. Okay.
Okay.
Okay, I think I have another question from the chat box. Explain once more what is. Okay, AF stand is the distance from the epicenter. So you have these seismometers now. Just I show you. So, for example, this is your epicenter. The distance from each seismometer from the epicenter is called AF stand. Okay.
Sir,
Any
and also the fractal concept, I didn't understand.
Okay, we will explain what fractal concept is, but I'll just give you one uh, quick understanding. I mean, we'll discuss about it later on. Okay, so there are phenomena in nature. Okay, there are phenomena in nature which follows fractal rule. What fractal rule essentially defines that suppose I'm looking at a population of data. There are some small, there are some mid-size, yeah, any data, and there are some large. Okay. Now, if I plot log frequency versus log dimension, okay, say for example, here the dimension is the radius of the particle. Okay. What I will observe that the smaller particles are occurring at a higher frequency, and the larger particles are occurring at a lower frequency. Okay. Now, if I do log f by log d, what I will observe that they actually follow a straight line. Log frequency versus log d. Okay. They follow a straight line. And you can actually calculate the slope of the line. And this the slope of the line m called fractal dimension. This can happen in any natural phenomena. You can read about fractals. If you type in Google, you will find it. Okay. So earthquake's magnitude is a fractal. You see the higher magnitude earthquakes occurring in less in numbers, and lower magnitude earthquakes happen in more in number. Another fractal, important, beautiful fractal is, say, for example, if you look at the ribs of a leaf, then there are smaller ribs as well. Now you can take the length of the log of length of the rib versus its log of frequency. Yeah, that is also fractal. Yeah. Recently, from my lab, we have proved that you know the mud cracks that you observe in your uh, you have seen mud cracks, right? The ones that you there are plenty of them around the campus
Yes,
when
sir.
the mud dries and mm,
After
forms these
the rain
beautiful
of summer.
polygonal cracks. Now you have
Yes, sir.
seen them, na? So we
Yes.
have recently shown that they are fractals too. So there are plenty of natural phenomena which follows this beautiful rule that the smaller numbers here are higher and the larger dimensions are lower in numbers.
Okay.
And that's what fractal is in a very layman's language. You can read all about fractals. People do PhDs on fractals and stuff. So it's a beautiful mathematical expression which is followed by plenty of natural phenomena of the nature. One of them is earthquake's magnitude.
So what was the x-axis in the log?
X-axis is, for example, here I am. For example, here in the first example, I have plotted, say, for example, the radius of the or the diameter of the grain. Okay, and here I have plotted the length of the rib, okay,
Yes.
any dimension. Here for earthquake, it is the magnitude, log of magnitude. Okay, and
Okay.
here also log of frequency.
Yes, sir.
So it's any dimension that that would be you can test it whether it is fractal or not. There are plenty of things which are fractals in nature.
Okay, sir.
Even if you have the faults that we have just talked about, in a large area, if the faults are of same generation, we'll talk about it later in structural geology. But for the timing, I can just give you an example. You know, if there are like thousands of faults in an area or fractures in an area, that those are also fractal. The amazing thing is it starts from the as humble as a it's not humble. I mean, the leaf of a particular plant is very complicated and intricate if you think about it. But then try look at a tear up in any leaf, and try look at its the structure of the rib. You can look at it under a microscope. It will be even more fascinated. And see, you can do your exercise by yourself. Take any leaf, and which has a lot of ribs. The important thing is it is a statistical test, so it has to have a lot of data, right? So a particular leaf which has a lot of ribs, and then you can do this, you can practice it and see if the leaf that you are examining follows fractal or not. Simple thing, you have to measure one dimension and then measure its frequency. How do we measure the frequency? Say for example, I have taken 5 minutes more. If anyone has a class, you can leave, no problem. Okay, it's anyway recorded. But as you have asked, so for example, you know, any dimension. Say for example, 0 to 2 centimeter, I have 10, or I have 1,000. Okay, uh, then 2 to 4 centimeter, I have 500. Okay, 500. 4 to 8 centimeter, I have how many? 40. Like that, you have to make a table and then you have to plot it in Excel, just the interval. Then you have to do but then you have to take a log here. You can take a len or log, doesn't matter. But do the same for both, okay? And then take a log here and see if they form a straight line or not. Because if there are plenty of data, you will find that there is a little bit of scattered, but then also still it will follow on a straight line. And then and then you can take the slope of it. and that would give you the fractal dimension for that particular parameter.
Okay, sir. Thank you.
All right. Any other question,
Sir,
Rahul? Yeah, Rahul.
yes, sir, I had a doubt, sir.
Yeah, tell me.
You said that with the increase in magnitude, can you show that diagram again in that
Which one?
uh, pres- the Richter scale one?
Okay.
Yeah, yeah, that one.
Yeah, this one.
Huh, this one.
Okay.
So in this, you said that the we take S&P difference, right?
Right.
The difference in which they arrive.
Yeah.
So the higher the magnitude, so the difference will be higher, right?
No. Why?
Shouldn't it like shouldn't it be?
No, it will not be. See, look at this diagram. Okay. You see, this is here. Here the difference between P9 and S9, right? This is time interval. You see the S wave magnitude and compare it with S wave magnitude here. It's not varying.
Okay,
It
okay,
is it is not related. Let's put it that
okay,
way.
okay, okay.
It is just the difference between the time of arrival. Amplitude is the ground motion. Okay, the motion that you are observing on your seismometer. This one. Yeah, this is the amplitude. This is the amplitude, and this is the difference in time. They are not related.
Also, the difference between their speed is because of the P wave travels in one medium and
No,
S
they
wave
are
travels in different
in
medium.
that station. They have traveled in the same medium, na? P wave
But
and S wave has traveled through the same medium
so why is there a difference in
because the
speed?
velocity is different. We
Oh,
calculated velocity in the last class. You remember?
yes, sir, I
Look
remember
at
that,
these
but
two expressions. Which one has a higher velocity? Which one is more? P wave
P,
has a higher velocity
P,
through the
P.
same medium. Hence, there is
Yeah,
a time interval difference. Got
yeah,
my point?
yes, sir.
The medium is the same. So their
Hmm.
bulk modulus, Young's modulus are the same. Yeah, but their expressions are different. The velocity expressions are different. So the velocities are different through the same media for P wave and S wave. P wave travels much faster than S wave.
Okay.
Okay. Anything else? How can we measure epicentral? We just talked about it, so on. You see that you have to. We talked about this now. So this is your P wave arrival time, and this is your S wave arrival time. You just connect it all of them. Wherever they meet, that means there is no distance between P wave arrival time and S wave arrival time, and that is the point where is your epicenter, right? Because at the epicenter there will not be any distance traveled by the waves. Okay, so they will fall over one another, right? Will fractal phenomena give rise to another fractal phenomena? I'm not exactly sure what you are asking. If you give me an example, then I can
Uh,
perhaps
sir,
give you.
like I was just wondering, like since you mentioned about faults and stuff, like I
Mhm.
was just wondering, and we're discussing earthquakes as well, right? So,
Right.
so in that sense, like see, like since the faults are fractally distributed, like and the earthquakes are also fractally distributed, I was just wondering if,
Whether
like,
they have relationship or not, right?
yeah, yeah.
I mean,
So
whether
that,
these two fractals have relationship or not.
yeah, yeah.
I don't know exactly, Ashwin.
I
Someone
was
has
just
to
wondering,
test.
if, such if something, if two things are related and one is fractally distributed, that will give
Yeah.
rise to another. It was just
Well,
something
it,
that
it,
I
it
mentioned.
could happen, but I don't know exactly how. The length of the fault is a fractal phenomena.
Okay.
Similarly, the magnitude of earthquake is a fractal phenomena.
Yes.
Larger the faulting, you can expect a higher magnitude earthquake.
Yes.
Yeah.
Yes.
And then, of course, but that is not always one to one. Huh?
Yeah. Yeah.
So
Yeah.
it's something that can be tested, I think.
Okay.
But I don't have a ready-made answer for you at this moment whether they will be related or not. That's a good thing to investigate maybe in future. Yeah.
Yes, sir.
Yeah. I don't have a direct answer for you.
Okay.
But that's a good way of thinking. You can investigate that. Maybe someone has done some work around it.
Yes. I'll
Okay.
look at.
Yeah. Anything else? Okay, so I will just stop the class here then, and I will continue with the earthquake seismology in the pre-recorded lecture tomorrow. And on Monday we will start with next week we will start with the reflection seismology. Okay, thank you.